The cause of the far lands was not discovered until January of 2015, shortly after the addition of customized worlds which enabled us to see the noise scales for the first time. The far lands are caused by an integer overflow in the coordinates for two of the noise maps used in generating Minecraft's terrain. For all of the various Perlin noise generators that exist within Minecraft, a coordinate is initially calculated as a double by multiplying the block coordinate by the noise scale. This value is then cast to a 32-bit integer, which is rounded towards 0, that is rounded down if positive, and up if negative. If the value is larger than 2 to the 31 minus 1, the result of casting to an int is simply 2 to the 31 minus 1. The integer is then converted back to a double and subtracted from the original value to extract the fractional part of the noise coordinate. In normal areas, the fraction is always within the intended range of 0 to 1. However, when the noise coordinate is greater than 2 to the 31, the fraction will be much larger than 1. In fact, the fraction of the noise coordinate will be how many units the noise coordinate is past 2 to the 31, which is directly proportional to the number of blocks past the start of the far lands. As if that wasn't enough, the fraction value is then plugged into an equation, which simplifies to 6x to the 5th minus 15x to the 4th plus 10x cubed. This formula is used for quintic interpolation between 0 and 1, as its output in that range is monotonically increasing, and is also between 0 and 1. However, the function just blows up as the fraction value increases beyond 1, which causes the noise values to become very large. The rest is essentially random, being determined by the integer parts of the other two noise coordinates, which in the case of the edge far lands as seen here, are still within normal range. Essentially, what Perlin noise does is it interpolates between the values at the 4 corners of a square, or in the case of 3D Perlin noise, the 8 vertices of a cube, and uses the quintic equation to interpolate between all the corners or vertices. And the edges of the squares or the cubes would be the points where the noise coordinates are integers. Now, the two main noise generators used in generating Minecraft's terrain, known as low and high noise, are scaled so that one block is equivalent to 171.103 units of their highest octave. And 2 to the 31 over 171.103 is, wait for it, approximately 12,550,824. Now, the noise is also only calculated at blocks divisible by 4 on the x and z axes, and blocks divisible by 8 on the y-axis. And it is linearly interpolated in between. So this is why the far lands appear smoother and more natural looking than you would expect, given the rest of the information I just described. And the sampling intervals on the y-axis being twice as large causes the tunnels to appear stretched vertically. You may notice that the far lands look much more chaotic than the normal terrain generating up to them. This is because there are 16 layers, known as octaves of low and high noise, and the octave that causes the far lands is actually has the least effect when generating normal terrain. And the octave that has the most effect in normal terrain is actually the lowest octave, whose coordinates increase by only 0.005221 approximately every block in the case of low and high noise. The higher octaves simply add detail to the noise map. The noise also repeats every 256 units, and the octave that causes the far lands increases by 107.13 every block. Once again, so the smallest integer that can be multiplied by to get a whole number divisible by 256 is 256,000. And sure enough, the edge far land structure can repeat every 256,000 blocks on the other axis. And so sure enough, the edge far land structure can repeat every 256,000 blocks on the other axis. You may also notice these 4-block long artifacts at the beginning of the far lands in the positive directions. These are caused by the values of the noise at 12,550,828 being much larger than at 12,550,824, which in turn is much larger than at 12,550,820. What's more is that the noise generators use a random offset from 0 to 256. In most cases, the random offset is enough to get the noise coordinate at 12,550,824 for low and high noise over 2 to the 31. But in some cases, it might not be enough. Such as here, where if that is the case, then the far lands will actually start at 12,550,825, as we see right here. If the random offset is just enough to get the noise coordinate at 12,550,824 over 2 to the 31, then the initiation of the edge far lands will look rather smooth, as is seen here. If the random offset is enough to get the noise coordinate at 12,550,824 well over 2 to the 31, as it usually is, then the far lands will clearly start at 12,550,821, as the noise is once again only calculated at blocks where both the x-coordinate and the z-coordinate are divisible by 4. And the noise is interpolated in between, and the noise values at 12,550,824 will be much larger than at 12,550,820, because again, with the quintic equation, even plugging in a value of a couple hundred into the quintic equation would already give you a number on the order of 1 trillion. That's how quickly it will blow up after the noise coordinate starts overflowing. Also note that when there is a tip, whenever there is a tip of an a tunnel or an artifact in the edge far lands, as is seen right here, it will always be at a coordinate on the other axis that is divisible by 4. Similarly, whenever a layer is 1 block thick in the corner far lands, it can only be, or when an artifact is even 1 block thick in the edge far lands, it can only be at a y-coordinate that's divisible by 8. An interesting artifact of the corner far lands is the diagonal lines that can be seen carved into the floors and ceilings of layers. Sometimes up in the top layer, these can appear as cliffs, like we see here. These all originate at the initiation of the corner far lands, and are caused by calculations using a grad function, which takes 2 of the 3 noise coordinate fraction values and either adds one to the other or subtracts one from the other. Which 2 fractions are added or subtracted, and whether they are added or subtracted, is dependent on a random number from 0 to 15, which is determined using each of the integer noise coordinates modulo 256. In the corner far lands, the x and z integer noise coordinates are always the same value, that is 2 to the 31 minus 1. So it only depends on the y noise coordinate, basically. Yeah, this is another thing I forgot to mention, actually. So the reason why the edge far lands appear striped is because the noise coordinate is always 2 to the 31 minus 1 on one axis, but on the other axis it varies because it is still in normal range. But the corner far lands, both axes integer noise coordinates are both always the same value, which is what causes the relatively very flat terrain. Now here's a couple things I forgot to mention. In the edge far lands, the noise values are roughly on the order of 6 times the fraction to the 5th power. However, in the corner far lands, the quintic values on the x and z axes would be roughly multiplied together. So when both the x and z coordinates are the same, the noise values would actually be expected to be on the order of the fraction to the 10th power. Additionally, since the integer noise coordinate is rounded towards 0 when casting, it will be rounded up in the negatives, so it will be decremented by the part of the code that is added to make sure that the fraction is always positive. However, in the negative edge far lands, this causes the integer noise coordinate to wrap around from negative 2 to the 31 all the way back around to positive 2 to the 31 minus 1. And that right away puts the fraction at negative 4.295 billion approximately. This is why you usually don't see as many diagonal lines in the other 3 quadrants of the corner far lands. Of course, there are a couple here. but there are just not as many as in the usual. In the corner farlands on any given map, there are two distinct regions. The x side, where the fraction on the x-axis is much larger than the fraction on the z-axis, and the z side, where the fraction on the z-axis is much larger than on the x-axis. Everything else in the corner farlands is essentially an interpolation between the two, and because in the middle the fractions are roughly the same, so the terms related to them in the calculations have roughly equal effect. But as we go toward the x side, the x fraction related terms weigh more, and as we go toward the z side, the z fraction the terms related to the z fraction will have more weight. And the diagonal lines being caused by calculations of the fraction value follows basically just from intuition, because we know everywhere in the corner farlands the integer noise coordinates are the same. Both the integer noise coordinates are the same everywhere in the corner farlands, both to the 31 minus 1. Now, there is a certain way the quadrants, or the four quadrants, are all related to each other, due to the noise, partly due to the integer noise coordinates also being positive 2 to the 31 minus 1, and in all of the other quadrants as well. So if we teleport to the northeast quadrant here, you will see that its z side is pretty much exactly the same as that of the main quadrant. But as we go toward the x side in this quadrant, it gradually morphs into an inversion of the x side of the main quadrant. The reason for this is because if one fraction value's sign is inverted, its corresponding terms in the grad functions will be inverted, which will invert the signs of the grad function results if it is the larger one, or have a negligible effect if it is the smaller one. And one of the quintics which are multiplied together will also be inverted. So on the z side over here, we see that two signs are inverted, which is why we get the mirror image. But over here, effectively only one sign is inverted in calculations, which is why we get the inversion. And indeed, and if we teleport to the northwest quadrant, we see that it is an exact inversion of the southeast quadrant. And by that, I mean that if we switch which layers are air and which ones are solid from the southeast quadrant, we get the northwest quadrant. And the southeast quadrant in this map is one of the thinnest corner farland spawns I've seen, which makes the northwest one of the thickest. And if we do teleport to the southwest here, go to the southwest quadrant here, we see that it mirrors the x side of the main quadrant, and its z side is an inversion of that in the main quadrant. Another seed where this inversion phenomenon is apparent is -3 quadruple 4 7 5 0 8 5 9 7 7 8 6 3 8 1. Here you can see if we teleport, if we're in the positive quadrant, if we teleport to the negative quadrant, you will see that these areas, that these caverns directly correspond to in the negative quadrant, directly correspond to the large hills in the positive quadrant. And if we head up to the top here, we see that these low areas directly correspond to the floating islands in the positive quadrant. Now note that the x side may not be exactly mirrored in the southwest quadrant, and the z side may actually not be exactly mirrored in the northeast quadrant, like we actually see in this seed. Like you'll see right here, if you remember, in this seed, we never had the floating islands weren't actually this high on the z side in this seed in the main quadrant, yet over here they are for some reason. And that actually happens when the noise value at that layer, as that one fraction value gets much larger than the other one, is going towards 0. So yeah. There's also some farlands in the nether which look identical to the overworlds except with nether features. And in the sky dimension. Note that the sky dimension farlands look much more stretched horizontally than the overworld and nether's farlands. And the reason for this is because in the sky dimension, the noise is actually sampled every 8 blocks. It's actually sampled every 8 blocks along the x and z axes rather than every 4. And it is sampled every 4 blocks on the y-axis rather than every 8. So basically the horizontal and vertical noise sampling intervals are switched. Note that this is identical to the shape of the end farlands in later versions, which we'll show later in the video. In older versions of the game, at 32 million, the game would no longer bother to run the world. And every block after this was essentially a ghost block, which you could not interact with and that would have no clipping. In fact, this limit is what would become the world border we have today. There is a statement floating around that the terrain no longer generates after this point, and only air blocks of detectors of the surrounding terrain generate. But what actually happens is the terrain does generate, but it is considered air by functions in the game's code that deal with blocks in the world. There is also a wrong theory going around that this is a Java limitation, when in reality it was a boundary intentionally defined in the game's code, most likely to allow the complete avoidance of the original farlands, which would just appear as a stone wall at 2 to the 25 with nothing beyond that. It's really not that interesting. It is also incorrect to say that block physics and lighting stopped working at this point, because what's actually happening is that they would function all the way out to the 32-bit integer limit, but the game just doesn't bother to run block physics or lighting past this point, because again, they are intentionally coded to only operate within this limit. Also note that for whatever reason, the fake chunks can cause a lot of lag, with entities and lighting and all that stuff ruled out, the only plausible explanation is that the game is searching for a valid block to spawn animals or something, but can't find any as the intangible blocks are considered air. However, this limit can be easily modded out, allowing trees and entities and lighting everything to all appear out to the 32-bit integer limit. Remember the tidbit earlier about the noise octaves? Well, it turns out that for every addition, there is another set of farlands for every additional octave of low and high noise. The last of which does not overflow until over 411 billion blocks out. However, if we teleport to 25,101,648 on both axes, we see there is no visible effect, as the noise values of the first octave by this point are already much larger than those of the second octave would be just after it overflows, because the noise values of the second octave here are comparable to the first octave at the beginning. Those are the first octave at the beginning of the farlands. However, there are some visible manifestations. If we teleport to negative 25,001,648, on one axis, you will see that there are some small shifts in the edge farlands' strips of terrain and tunnels at that exact point. And that's again because of the fraction of the second octave going straight from like a normal value to minus 4.295 billion, unlike on the positive end where it just starts in the hundreds. It just starts off in like the hundreds. And in the seed Gargamel, whose corner farlands look pretty average except for the plateaus being blockier than usual due to the grad functions for that noise generator at level 120 coming out in such a way that the various terms cancel out. If we head to 29,145,800 on both axes, you will see that the plateaus actually end in this diagonal line that is actually different from the usual diagonal lines of the corner farlands. And if you were to use coordinates going, you'd see it's actually a mathematical curve. And this is actually a visible manifestation of the second octave corner farlands. The farlands look different in early InfDev versions. In the original InfDev build, the farlands were just a stone wall at 33,554,432, with chunks beyond just completely filled with stone, and that was it. The farlands became much more familiar in the March 27th, 2010 build. However, these farlands, as seen in the world generation of the InfDev April 15th, 2010 build using the modern beta bond, look considerably different from the later farlands. In general, these farlands appeared kind of denser than the later farlands. The look of the farlands would change throughout the InfDev builds, which was reflective of the fact that the terrain algorithm was still very much a work in progress at that point. In general, the edge farlands would just appear sort of kind of flatter and thicker, and the corner farlands would also have thinner layers which appeared more densely packed. You may notice that the early InfDev farlands can actually start at 12,550,822 or 12,550,823 like we see here, while in later versions it's only possible for the farlands to either start at 12,550,821 or 12,550,825. That's because instead of being sampled every 4 blocks in the x and z axes, the noise in these versions was actually sampled every block on all 3 axes. Like on the z side here, we see that the farlands also start at 12,550,823 as well.